All right, rules of exponents. Why are we doing rules of exponents? Let me tell you why. Has anybody heard of outer space and the distances traveled? When we deal with scientific, I'm often made fun of at the school. He stopped with this. I want to know why. Earphones off. Earphones up. It's going to be okay, Lavieta. 10 minutes without music, you're going to survive. Trust. You too, Rios. Come on. That's what I have for it. I'll let you put it on that. I'm often made fun of for driving to school in a scooter. You may have seen the school kid driving around Pomona in a scooter. No, I drive a scooter. So it's a 50cc scooter, very small scooter. I drive 8 miles to work and from home and back, and I'm made fun of. The highest speed that my scooter can travel, it's 45 miles per hour. It doesn't go any faster than that. In other words, I can't drive down the freeway, nor do I need to because I just get here on the streets. It's an easy 8-mile drive from the city of Chino. Anyway, pretty much every car on the road goes faster than my scooter. But there's vehicles that go faster than cars. Can someone think of a vehicle that goes faster than a car? Motorcycle. What goes faster than a motorcycle? Yeah, that's a good one. I saw one yesterday in Arizona, F-16 flying over Arizona for a Memorial Day celebration. It was no joke. It was going like 800 miles per hour. What's faster than the jet? Rocket. Airplanes are a lot slower. It's airplane engines. Rocket would be faster than the jet. When you start going Mach 1, Mach 2, Mach 3 speed, when you say Mach 1, that's faster than the speed of sound. Now, what's faster than the speed of sound? The speed of light. Let me talk about the speed of light just a little bit, and let me, if I may, boggle your mind to some degree. Watch this. My scooter travels at 45 miles per hour, high speed. The speed of light, check this out, the speed of light travels, not at miles per hour, but it travels 186,000 miles per second. Not miles per hour, not even an hour, but for 1 second it travels 186,000 miles. Now, when we talk about, like when scientists have to talk about distances in outer space, they talk about light years, and I want to get into what a light year is. It's stunning. It's stunning. Let me tell you what a light year is. Watch this, Lizana. A light year. In other words, when we start studying outer space, distances are so vast and extreme, it doesn't make any sense to measure distances in miles and in feet and the types of units we're used to here on Earth because they're just so big. So the scientist has come up with the concept or unit of a light year. And what a light year is the distance that light travels in 1 year. Let me say it again. You want to know what a light year is? The distance that light travels in 1 year. Now, it travels this fast in 1 second. How would I figure out how much light travels in 1 year? How many miles? Well, 186,000 miles per 1 second. How many seconds are there in an hour? Or in a minute, rather. So I have to multiply this number by 60 to get the miles per minute. How many minutes in an hour? So I have to multiply that again by 60 for miles per hour. How many hours in a day? So I have to multiply that by 24 for... What happened?
6 to 12 hours in a day.
Are you going to forgive him, Medina?
I don't think so.
That's evil. That's evil for him to say that, huh? So 24 miles per day. How many days in a year? Miles per year. When you multiply all this garbage out, that's how many miles 1 light year is. So look at, watch this. 1 light year would be after you multiply all this, that's how many miles 1 light year is. And when we deal with distances in outer space, we talk about billions and billions of light years. the amount of miles that encompasses staggers the mind, and maybe, if you really think about it, it may cause you to crawl into a fetal position in horror and dread. How big and vast the universe is. Well, how big? What? Just multiply this out. So the number, you want the number? I think you got it. How many miles is 1 light year? Hit it, Lavieta. Extra stem, by the way. We got
4.9.
e to the what?
9.
Nice. Watch this. That brings us perfectly into our lecture today. So Lavieta multiply all this garbage out, and you got 5.9 e to the what? What power? Okay, that's a scientific notation because the numbers are so big, it doesn't make any sense to waste a lot of ink and put in a bunch of zeros after this. Watch this. So that means this. 5.9 times 10 to the 9th power means I'm going to move this decimal over 9 times to the right. So 5.9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so let's see. This is millions, so this is 5,900,000,000 miles would be 1 light year. 1 light year is 5,900,000,000 miles. And scientists talk about stars and planets and other solar systems and galaxies that are, watch this now, put your seatbelt on, that are billions of light years away. And this is just 1 light year.
Ooh.
Like my heart is like palpitating. That's the distance is so immense and so vast. It's almost scary in one sense. Stunning. Now, this whole thing about e to the 9th power is what we're going to get into. When numbers are so big, scientists need a method to communicate these big numbers called scientific notation. So what Lavieta did, this number in the calculator, 5.9 times 10 to the 9th power. Notice that exponent. We have to learn how to use exponents and the rules of exponents when we do calculations. This is like done in science all the time. It's done for distances and measures that are so big, and distances and measures that are extremely tiny beyond the naked eye. When you get into microns and microscopic organisms, microscopic units, we're talking about 5.9 times 10 to the negative 9th. Well, we actually have to move the decimal to the left now because we're getting into tinier and tinier units of measure that are beyond our electron microscopes sometimes. So scientists have made up this convention of communicating numbers called scientific notation. That's why we're going to talk about rules of exponents. Here we go. So the title is Rules of Exponents. Here we go, Skibel. The title is the first one. Go to write number 1. Go to write 0 exponent. What happens if you run into an exponent that's 0? Okay, let's check this out. Go to write 0 exponent. That's the rule. And in words, you have the 0 exponent rule described in words right here. And then you have an example with numbers of the rule, and then you have an example which is variables, which is algebra. So you have 2 examples, one with numbers and one with variables. So the first exponent rule is the 0 exponent rule. I'll write this down. I can't. It's showing you the example with letters, just with a variable instead of numbers. So we call that algebra. Algebra is basically variables and numbers, expressing quantities with variables. So this is an algebraic example right here. Notice a to the 0 power is 1. And here's a numeric example with numbers. 4 to the 0 power is 1. It's real straightforward. Anything to the 0 power is 1. Except there's only one number in the universe. There's only one number in the universe that if you raise to the 0 power, it's not 1. Can anybody give it to me for an extra stamp? There's only one number in the universe that if you raise it to the 0 power, it's not 1. Lozano got the extra stamp. Remind me
I'm
at the end.
so done.
With what? because he won and you did it?
Yeah.
That's pretty cool. Interesting definition. Example 2. Negative exponents. What the heck do you do with a negative exponent? Write this one down. For any integer n, any non-zero number a to the negative n is a reciprocal a, and we just saw that word in warm-up. You and I just saw the reciprocal word in warm-up. This is why I did it in warm-up, to prepare you. So if you have 4 to the negative 2 power, you just take the reciprocal, because this is over 1. You reciprocate it and make the exponent positive. That's all a negative exponent means. How about the algebraic example? A to the negative n over 1. If I were to reciprocate it, you flip it and make the exponent positive. That's all you do. It's as simple as that. Next one is the product of powers property. To multiply powers with the same base, when I say base, I mean the same thing that's being raised. So the same base here is going to be the 4 and the 4. Notice how you have the same base. All you got to do is add the exponents if you have the same base. That's the heart of this rule. Here at the algebraic example, the same base would be a and a. Notice, a and a. If you're multiplying and you have the same base, all you got to do is add the exponents. It's as simple as that. Any questions so far? Last one for the day. And we'll do the last 3 tomorrow. This one's called number 4, the quotient of powers property. Quotient of powers property. Let a be a non-zero real number and let m and n be integers. Product means multiply. Quotient means divide. So notice how you're dividing with the same base. The same base here is 4 and 4 again. Notice the same base would be 4 and 4. Notice what you do with the exponents, and if you're dividing with the same base, you just subtract the exponents. It's 6 minus 3, so it's 4 to the 3rd power. Right, Ortiz? Phones away for that second sound. No, no. Thank you. And here's the algebraic example. Notice the same base, a and a again, but this time we're dividing. So far, so good?